So next we'll study ovipole with n. So by ovipole with n, we will only study ones which are strongly tame, which means that you have some compact ovipole with boundary, and then you look at the interior of that. Okay, so I mean, of course, there are very complicated non-compact ovipoles, but we don't want to study that. So an end is a boundary component of OBA. So in this case, we just use this definition, but there is a more formal definition. So end neighborhood is open set where U union this sigma E is for a boundary component. Sigma E is a neighborhood of this sigma E. Okay, so you can take that kind of approach and. So for example, you can take one with the principal geodesic boundary. So if you have a properly convex real projective surface and it has a principal geodesic boundary, then so each of the boundary components correspond to n and has a convex n neighborhood. Okay, so it will have a convex n neighborhood inside or outside. So that's proven by Goldman in 1990. So we can also add elementary annuli along the principal geodesic boundary component, and then you can and remove the other end boundary component, so you can obtain another end. Okay, so another type of end. So if you have these properly convex surface, actually but the So there's a neighborhood of the end that is a union of elementary annulus and the convex end neighborhood before attaching. So these are we're going to be what's called the lens cones. So they are called the hyperbolic type end by the Marquis. So he classified the end for the two-dimensional cases. So when you are working in this type of situation for 2 dimensions. I will start from the top of this page. So let's look at the horospherical and quasi-hyperbolic ends. So if you have a hyperbolic surface with a cusp end, then each cusp has a horospherical end neighborhood. So that is a quotient of Horo disk. Sorry, it's not Horo. By some sort of infinite cyclic cyclic parabolic group. Okay, so then so of course here again this is a tame end because you can compactify by adding the simple geodesic curve here. Of course, then the geometry is not the geometrical adding, but I'm just saying that it's still tame here. And then also you could have some non-diagonalizable positive eigenvalued holonomy. So this means that the eigenvalues are going to be at least 2, but it's not diagonalizable, both positive. Then then actually you can actually compactify by geodesic boundary, and these are what's called the quasi-hyperbolic holonomy. Okay, and of course these parabolic ones have only one eigenvalue, but there is one with 2 eigenvalues which are not diagonalizable. Okay, so those also exist, but these are all foliated by radial segments. Okay, so of course these are classified by Marquis also. Okay. Okay. So now we want to so that those are the 2-dimensional examples, and now we want to study deformation space of Cox ovipole with some ends. So here we want to look at the cases that these Cox ovipoles are not compact and has some ends. Okay, so this corresponds to removing some vertices. Okay, so and then the point is that you can actually deform these Cox ovipoles, and then you can find this phenomenon called cusp opening. So which was discovered by Benoit, yes. So first of all, Cox N orbifold is an N orbifold based on some polytope with silver boundary facets, and so whenever these on the side, it will side is either inside the singular locus or it could just be have been removed. Okay, if it's not in the singular locus. Okay, so it's just so what is the deformation space of projective structure on orbifold P hat is a space of all projective structures on P hat quotient by the isotropy group action of P hat. And so Bimberg made the big analysis of this in 70s, and Benoist continued this. And so for the points P of the P hat, we can always determine this fundamental polytope P. Of course, here I mean that the P is, of course, if you're given a projective structure, the P will be determined, but you can start with any sort of topological P and then ask the question whether it will admit this kind of structure, convex projective structure. I mean, making the P into orbifold first, into Cox orbifold first. So now, but what we wanted to do was we wanted to understand when this fundamental polyhedron is always projectively equivalent to a fixed P, okay, fixed convex polytope. And then this is called the restricted deformation space. So it's dp written by p hat. So okay, so that's the thing that we wanted to understand, and so the ones we could understand was orderable case. So we studied we can order these sides. So these are only for three dimensions. Okay. So we order the faces, size of P, so that each side has no more than three edges, which are from which have order 2 or is included in the side of higher index, higher order ones. Okay, so so 3 is an important number here. So you don't have anything coming from 2 or the side of higher index is less than 3. So if you start with some convex polyhedron and P hat is given a normal type Cox orbifold structure. Here, the normal type means that it's not a product or it's not a spherical or it's not affine. So I forgot to say affine in the paper, but it's not affine also. Then the KP is KP be the dimension of what P, then the and suppose that P hat is orderable, then dpp is actually some smooth manifold of this dimension. If it's not empty, of course it could be empty, and E is a number of edges, and E is a number of edges of order 2. Okay, and of course KP is usually going to be 0. So except for something like pyramid here. Okay, and then F is a number of faces. Okay, so these numbers right. So that so the basically the condition here is that the this orderability is that these if you want to compute some differential of the equations, you just show that these sort of ones which can be done by triangulable conditions. Okay, so this is really the triangulability of the equations. That's the only thing that I'm using here. So the proof is that so you have some you have only freedom is the reflection points. So the reflection is always determined by the reflection plane and the points of reflection, and then it's so this is the underdetermined case in the case of algebraic equations, and the other cases are usually overdetermined, and it's also something that so that some triangulability will work in the differentiable setting. So so then these total deformation space will fiber over some open subset of the subspace polytope polytopes combinatorial equivalent to P. Okay, so this when I mean by fibers, I mean that it's not a really vibration. It's just that some sort of a mapping exists with the constant dimensional fiber. Okay, so those are the first ones we can study. So these are actually some things that Benoit did for the prism, and then I generalize this to these cases, and and then my case actually did a special case of these sort of things. So you take a tetrahedron and cut off vertices. You can keep iterating this. So the resulting polytopes is of course called the truncation polytope. Okay, so this is only for dimension 3, of course. Then the Marquez result is that if you have these compact ones, hyperbolic Cox 3/4 based on truncation polytope, then this is diffeomorphic to R E minus E2 minus 3. And so I'm not saying his full theorem, but I'm just saying the hyperbolic part here. And and the proof is very sort of combinatorial and it's algebraic. Okay, so you can track these using algebraic system very easily. So these are all for the compact cases, but the compact OV4. But of course, my work. So this work will also will be for the you can work for the ones which are not compact. Okay. And then the next type of result was when you have a ideal or hyper-ideal convex Cox 3/4 p hat. So you take some polytope here, and then which admits a hyperbolic structure. So, for example, you take a polytope with all the vertices on the sphere of infinity in the Klein model, so that those things exist plenty. So. And then suppose you can give a sort of orbifold structure to this, and it admits a hyperbolic structure. So here, so that's what I mean by ideal ones. So hyper-ideal ones, you can allow to have a vertices outside these hyperbolic plane space in the so in the projective model. Okay, so right. So we didn't of course publish the hyper-ideal version, but we only published the ideal version. Um, and of course, all the edge orders has to be bigger than equal to 3. Though nothing has to be 2. And of course, this means that there's no vertices, elliptic vertices, so there's no vertices inside the hyperbolic space. So like so the finitely many of them will not exist, like 2 to n or these kind of 2, 3, 5. They don't exist in this kind of setting. So all the vertices are sort of ideal or hyper-ideal, which means they are removed. Okay. So then this deformation space has dimension E minus 3 and it's smooth at the hyperbolic point. And the proof is again the very precise infinitesimal rigidity. So again, this uses the fact that the H1 of the boundary rigidity will imply the smoothness. Okay. So that's some relation to the work of Porty here, but okay. Okay, and then of course Chaudhary and Lee, and we did show that the order of a compact hyperbolic Cox orbifold, there's only 5 of them, so it's tetrahedron prism and 3 other type, and so that's kind of disappointing. But of course, if you have ideal vertices or hyper-ideal vertices, then there are infinitely many of them. So we still have some things to do, and so orderability is of course more general than truncation or for conditions. Of course, the Marquis result is not just for hyperbolic ones, so he has a lot more than what we have here. But uh, okay, and then the right. Okay, and then the next one is on the cube. So we look at all the hyperbolic cubes. So this means hyperbolic cubes with the orbifold structure and has a hyperbolic structures, and and it's also compact ones. Compact, it gives you compact cox orbifold. So the dihedral angles are always pi over 2 or pi over 3 in this case, and so up to symmetry there is a 34 of them. Okay, and then you can show that 10 are projectively deformable relative to mirrors. Okay, so we do the restricted deformation space, and then so the remaining ones are rigid relative to mirror. So once you fix these projective class of P of the cube, and the deformation of the is 3/4. Some of these are not projective bending. So one way to obtain the deformation always was to use these Johnson and Wilson deformation along totally geodesic subspaces, and that we can show that these are not really projective bending. So these are just trying to get more examples of bendings. Okay. And then the next type of result was that if you have a compact Cox orbifold, of course these are all three-dimensional, is weakly orderable. If you can order the faces so that each face contains at most 3 edges of order 2 in the faces of the higher indices. So in this case, what you need is it not only comes from the these order 2 edges has to come from the faces of higher order. Okay, so if you don't have that, then this is weakly orderable, or it's based on truncation polytope. So there are many compact hyperbolic 3/4 satisfying these conditions, and then we can show that so for these ones, actually the deformation space is smooth manifold dimension E minus E2 minus N. At the hyperbolic point, if N is 3 and and the Q is weakly orderable, or Q is based on a truncation polytope. Okay. But of course, this theorem, we don't really have a smoothness outside the hyperbolic point. So hyperbolic point is when this is at the when it comes from the hyperbolic representation. So we want to actually generate this somehow, or investigate further these kind of things. So some pictures of these prism deformation that Benoit did for the example. So actually this is an animation, but I couldn't include it here. Okay, so so that's the end here, and then there are some references you can see here. What I mentioned. So of course these are sort of not really complete. So you should ask me if you want to know more. Okay.